Hi, in this video I'm going to demonstrate how to determine the correct pinouts when there's no label on the relay. So how do you know which are the coil wires? How do you know which are the normally open or the normally closed contacts? Right, when the relay has a window like this, it's quite easy to just follow the contact and see which terminal goes where. In terms of a relay like this, there's no description or drawing to say which contact is which because you can actually see it through the window. But what happens when you've got a relay that looks like this? There's some pins, there's no diagram or indentation on the underside of this relay. However, on the top there is a part number. Now you could go and look up this part number and find the pinouts. But sometimes you'll find that the relay has been rubbed off, or it is an old relay and some of the signage is off, and you need to quickly check the terminals, which are the coil wires and which are the contact wires. So I'm going to quickly show you how to do this. I'm going to start with a small relay and then I'll show you some other examples. All right, you will need a multimeter for this, and I do have a DC bench supply which I'm going to use as well. Now the first thing that I do is I just inspect the underside and try and apply logic. Right, so here's the underside of the relay, and it seems like the coil wires are probably that and that. However, the coil wires could also be that and that. It is unlikely that this is a coil wire because it is sitting alone. Usually the coil wires would be together or on the same side of the relay. That is why I think those two are the coil, or that and that is the coil. The way I'm going to do this is I'm first going to measure the resistance between there and there, then I'll measure the resistance between there and there. Then I will just check the resistance between the other terminals just to make sure. Right, so I'm measuring the resistance between those two terminals which are close to each other, and you can see the meter says 0.7 kilo ohms or 740 ohms. That must be the coil. If I measure between there and there, you can see it's an open circuit. If I measure between there and this one now, also open circuit, there and there, also open circuit, and finally there and there, also open circuit. So that means just from measuring the resistance, there and there is a coil. So if I apply voltage there, I know that I'm going to be able to hear the relay click. So that's another way to test it, is to listen when you apply a voltage. Now over here I have a bench supply, and I'm going to assume this is a DC relay. And what I'm going to do is I'm going to start increasing the voltage slowly like that, but I'm also going to limit the current to 0.5 amp. And most relays operate from a voltage lower than the voltage that is imprinted on the side, but the common voltages for relays are 6, 8, 10, 12, and 24, especially for the DC relay. So what I'm going to do is I'm going to start at 5 volts and then I'm going to increase it, and then what will happen is you often hear the relay going brrr, making a brrr sound, telling you that it is close to the correct voltage. Right, I've connected my supply across those two terminals and I'm gently increasing the voltage, listening for a click, but also watching the current. And it actually already clicked. And this relay operated at 8 volts, and this click started at 8 volts. So that's telling me that this is probably a 10 or 12 volt relay, but I know from the packaging that it is a 12 volt because it's written there. But remember, I said I'm trying to work this out if this was rubbed off, or if you were trying to work out the voltage and the contacts without having any of the information. Right, so the relay is operating nicely. Now the last thing is to just check the normally closed or the normally open contacts. Now in this case there are only 2 additional contacts available to me, which means this must be a normally open relay, because as I've got my meter here at the moment, right, you can see the meter is saying open circuit, and when I activate the relay, you can hear that sound is telling me it's a short circuit. So using a process of elimination, I've worked out that those two are the coils to activate the relay, and the normally open contacts is that and that. But what happens if there are more contacts? Right, so over here I've got 2 different relays. Notice the one does have a little diagram underneath, so you could work out which pin is which from that diagram. But look at this one, there is no diagram underneath, and there's no model number on this relay. So how would you work out which pin is which? Right, so I'm going to apply the same principles now. You can see 2 leads here are close together. So these are probably the coil wires. However, that and that could also be a coil wire, and that could also be a coil wire. So what I'm going to do first is I'm going to measure the resistance between there and there. Then I'm going to measure the resistance between there and there, and then there and there. Hopefully one set will give me a coil resistance value. All right, so this was quite lucky. The very first terminals I tried gave me 318 ohms. That is a realistic coil resistance. And if I try other terminals, let's see, between there and there, open circuit, so it's not that. There and there, open circuit, there and there, open circuit. I can already tell that these two are the coil wires because of the nature of the relay. The coil does not touch any of the contacts. Now, to determine which are the normally open and which are the normally closed contacts, I will use the meter again. So these two are the coil, which leaves me 3 contacts here. So 2 of these must be a short circuit and 2 of these must be an open circuit, because relays are either normally open or normally closed. So if I go between there and there, right, so that is an open circuit. I'm going to put it to continuity. It's going to make a buzzing sound when there's a short circuit. So now I'm going to go between there and there. Also open circuit. So now what I'm going to do is put that back, and now I'm going to go between that middle pin and this one. Right, so there is my normally closed contact. That means when I energize the relay on these 2 terminals, this circuit here will become open circuit. I'm going to apply the same logic. I'm going to start with a low voltage and start increasing it slightly while having current limit. Right, so we can see that I was correct when I apply 10 volts to this relay. This is probably a 12 volt relay. We can see that it's going open circuit, closed circuit, open, closed. So now the question is to determine which are the normally closed contacts. Right, now I've tried these 2. It's not these 2. So I'm going to put this one back. And I now see it's these 2. Right, there you can see this is the normally open contact. When I activate the relay, they become closed circuit, open circuit, closed circuit, open circuit. The other contacts are the normally closed. As you can see, it's closed circuit, open circuit, closed circuit, open circuit. So I've effectively worked out the pinouts of this relay. Right, just some additional comments. If you've got a relay that's got no labels, no diagram, then checking the resistance is a good sign for which is the coil. Like if I put it on resistance, 140 ohms could not be normally closed. Normally closed would be 1 or 2 ohms or even 0.5 ohms. Here it's too high to be a normally closed contact. So I know immediately that this is the coil section. Often the coil section is on one side of the relay. While it's not a rule, as you can see how the contacts are all on that side and then the coil side is sitting here. And there's an example of the resistance, 259. But if you measure the resistance of a normally closed contact, you'll see that it is very low. There you can see the meter is measuring 1.5 ohms dead short. When it comes to more complicated relays such as this, I can also assume that the coil wire is on this side. There's the relay coil side, 150 ohms. But when we see these type of connections, it's almost in a line. It's usual that this, and this would be one independent section of the relay. So this would be a single pole double throw. And then again here, 1, 2, 3, a single pole double throw. So what we see is we'd have 4 single pole double throw relays within one housing. And in this case, because it's got the window, you can see it, but it is logical just by inspecting the pins. Now, the coil resistance also gives you an indication of the voltage that would be applied. For example, if I measure this coil resistance, you can see that it is 15 kilo ohms. And the higher resistance is telling you that a higher voltage would be applied here. And this is an AC relay. You can see it even says there 220 volts AC. And the reason being is because the voltage applied is so much higher, we have a much higher resistance. Otherwise, the current moving through the coil would be too high. That's also an indication of whether it's an AC relay or DC relay. Generally, DC relays have a lower resistance. So if you compare this 15 kilo ohms to this 24 volt DC relay, look at the resistance on this one. It's 1 kilo ohm. And this is a 24 volt relay. And this 6 volt relay, have a look at the resistance. Resistance is even lower. Why? Because it's going to need more current to energize the coil, and that is why the resistance is lower, because the voltage applied is actually very low. This is only a 6 volt relay. While over here, this is a 12 volt relay, and you can see the resistance is 263 ohms. and going even higher. This is a 24 volt relay, and you can see the resistance getting higher again, 1 kilo ohm. Now, sometimes relays with a higher current carrying capability, see this is a 30 amp relay, you'll find that the coil current is a bit higher in order to open and close a higher current. So if you have a look at this, this is a 12 volt relay, but you can see the resistance is 85 ohms. While going back to this very small relay, also 12 volt, look at the resistance here, 700 ohms. Why? Because it only needs a very small current to operate this relay. So even though these are both 12 volt relays, the resistance is considerably different because this is a much higher current carrying relay, while this is a lower current carrying relay, which changes the amount of current that's required to activate the relay. The bigger the contacts, the higher the current that would flow between the contacts, needs more magnetic force to open those contacts and to close those contacts because they are mechanically bigger. Therefore, the bigger relay needs a higher current, even though it's just a 12 volt relay. The smaller relay can only open a smaller current, and therefore the contacts can be smaller, the coil is smaller, and therefore it uses a lower current, therefore the resistance is higher. So these are some logical things to consider when trying to determine the pinouts of the relay if you didn't have a drawing or the number was scratched off. Alright, I hope that was helpful, and thanks for watching, and cheers.